Problem 8.6. Compute the impulse necessary to bring to rest the 50 kilogram driver of an automobile initially moving at 25 meters per second. Alright, so we have driver. It has an initial momentum, p sub I. And the final momentum is 0. So the change in momentum, which is going to be the impulse, delta p, this is a one-dimensional problem, is going to be the final momentum minus the initial momentum, which is 0 minus pi. And so I'm assuming a coordinate system that goes in this direction. I'm not putting x subscripts on here, it's a 1D problem, but you can assume x subscripts everywhere. And so this is going to be equal to 0, put some units in here, kilogram meters per second, minus the initial momentum. Okay, so that's going to be the mass of the driver times the initial velocity. Minus 1250 kilogram meters per second. Okay, and the negative sign, of course, means that the delta p is to the left. That's the delta p. Okay, so we know from the impulse momentum theorem that this is going to be equal to the force times the average force times the time over which the force is applied, and clearly the force needs to be to the left to stop something that's initially moving to the right. Okay, part B says, it's a good segue into part B. Find the average force on the driver if the deceleration is accomplished gradually by the application of brakes over a 10-second interval. And so we have from the impulse momentum theorem, F average times delta t is equal to delta p. So in other words, the average force is equal to delta p over delta t, which is equal to minus 1250. I'm going to write this as Newton seconds here. Remember, Newton seconds are equivalent to kilogram meters per second. And now divide by the time interval, 10 seconds, and conclude that the average force is minus 125 newtons. And again, this means that the force is to the left. Part C, find the average force if the car is stopped in a collision that brings the car's seat to rest in 0.1 seconds, assuming the driver is restrained by a seatbelt. Okay, so we have the same delta p here. We're going to use the same equation again, but the delta t instead of being 10 seconds is going to be 0.1 seconds. Okay, so there is there's a factor of 100 between 0.1 and 10. So I'm expecting this to go up by a factor of 100. So let's do the calculation here. F av is equal to minus 1250 Newton seconds. That's the delta p that we had expressed in appropriate units, divided by 0.1 seconds. And that's going to be minus 12500, 12,500 newtons. It's much larger. Alright, so that brings us to the last question here in part C. And what are the functions of seatbelts and airbags in a collision? Okay, so seatbelts and airbags are essentially going to decrease the force on the passenger by increasing delta t. And so through this equation, the delta p is going to be the same because the passenger is going to be brought to rest. But the delta t is increased to decrease that, which of course is the purpose is to save the passenger from injury and from serious injury.